How do you protect? Oh, by the TV.
Fuka, thank you. Nice to meet you.
Can you hear me? Yes. Good morning, everyone. Welcome to the session on symmetric cryptanalysis. So we have 4 talks. The first one is called Algebraic Meet in the Middle Attack on Low MC. It's by Fukang Liu, Santanu Sarkar, Gaoli Wang, Willy Meyer, and Takanori Isobe. And Fukang will give the talk.
So, thanks for the introduction. So I will give the talk, Algebraic Meet in the Middle Attack on Low MC. So Low MC is a very famous family of block ciphers proposed at the Asiacrypt 2015. It was designed to be MPC, FHE, and ZK friendly. So one notable feature of Low MC is that its parameters can be chosen in a flexible way, including its affine layers, the key schedule function, and the number of S boxes per round. So Low MC is also well known for its feature of partial nonlinear layers. In this work, we focus on the cryptanalysis of Low MC, and the previous results can be classified into 4 types. We focus on the third type where 2 chosen plain text cipher test pairs can be used. And the attacks in this setting are related to the security proof of the picnic signature scheme, although it cannot threaten the security of the picnic signature scheme. So we improve the attacks in this setting by proposing a new technique called algebraic meet-in-the-middle attack. To understand our attack, it's necessary to first understand the difference enumeration attack proposed at the TUSEC 2018. So the general idea is indeed very simple. So giving two chosen plain-text ciphertext pairs, we can know its input difference theta 0 and the output difference theta r. Then we can enumerate and store all possible state differences theta I computed from theta 0. Similarly, we can also compute all possible theta I starting from theta r. And for each computed theta I, we can try to find a match from the pre-computation table. And once such a match is found, we get a trail. And the key can be simply recovered once such a trail is fully known, because the active S box will leak some information of the key bits. And in detail, let us consider the low MC S box. So for this S box, so each input difference theta x will correspond to, on average, 2 to the 1.86 different output differences. So let us consider the low MC parameters with m S boxes per round. Then if we want to enumerate all possible theta r starting from theta 0, we will obtain 2 to the 1.86 MR state differences theta r. Of course, this should be smaller than the block size n. Otherwise, it's impossible to have more than 2 to the m state differences, because it is an n-bit value. Similarly, we can also enumerate all possible theta 0 starting from theta r, and we will get the same number of state differences. Then, with this in mind, it's easy to understand the original difference enumeration attack. So by exploiting the feature of the partial nonlinear layers, it's possible to find a input difference theta 0 such that there's no active S box in the first R0 rounds. So theta R0 is also fixed. Then we can apply the above meet-in-the-middle strategies stated above for the next R1 plus R2 rounds. And we can get a unique difference transition from theta R0 to theta R. And we can get the unique difference transition differential trail from theta R0 to theta R. And this trail will be exactly the trail for the two chosen plain-text ciphertext pairs. However, there are drawbacks. So first, it is only allowed to have one differential trail survived after the match. So we only have one trail survived after the match, and this trail will be exactly the trail generated by the two chosen plain-text ciphertext pairs. Second, the key recovery is too inefficient. Of course, there is no problem for this attack because we only have one candidate trail, and we only need to perform the key recovery from one candidate trail. Third, the memory complexity is too high, and exponential in the middle, the number of middle rounds are 1. Then at Crypto 2021, an algebraic method was proposed. So different from the previous attack, they will not pre-compute a large table of state difference that are 0 plus R1 in advance. Instead, they will introduce, for example, here, they will introduce variables to represent the output difference for all the S boxes in the middle R1 rounds. Then we can know that R0 plus R1 will be linear in these variables, and we should know that R0 is fixed. So then for each challenge, R0 plus R1 computed backwards, we can solve a linear equation system to recover the difference transitions in the middle R1 rounds. However, the linear equation system cannot be underdetermined. Otherwise, there will be too many solutions, and we need to check all the solutions because we need to enumerate all possible difference transitions in the middle R1 rounds. And of course, we may say that we can, if if this is underdetermined, we indeed so R1 will be larger, but it is more expensive to increase R1 than to increase R2 if this is underdetermined. And the third, the key recovery is still inefficient. And because for the inactive S box here, we still need to perform the guess and determine technique. So there are still some problems left. One is how to further reduce the memory complexity of the original attack. And the second is how to further the middle R1 rounds for the algebraic method. And last, we need to further optimize the time complexity to retrieve care from recovered candidate differential trail. Because now we will have many differential candidate trails after R1 is increased. So this is our new attack framework. So it is easy to know where the difference it is. So in the middle R1 rounds, there will be two phases. The first is the offline phase, and the second is the online phase. And as the offline phase, we will do some pre-computation. And then as the online phase, given any challenge that R0 plus R1, we according to the pre-computed information, we retrieve the corresponding linear equation system and solve this linear equation system to recover the different transitions in the whole R1 rounds. So let us imagine that given any challenge computed backwards, we can directly determine some variables representing the output differences for some X boxes in the first R1 rounds, and for the variables representing the output difference of other X boxes, we can retrieve the corresponding linear equation system and solve it. So this is illustrated in this figure. So in a word, different from previous in the middle method, we will not store a large table of possible values of the challenges in advance. Instead, we will store in equations, and each equation will be associated with an index. Then, given any challenge, we first use it to compute the index and then retrieve the corresponding equation system, and then solve it to recover the four variables. So this is why we call it algebraic mid in the middle. And obviously, the memory complexity will be reduced because we do not need to pre-compute the values of the variables in the equation system. So let me give more details. So remember, notice our goal is to recover the different transitions in the middle R1 rounds given this value. And we can further split the middle R1 rounds into the first R1 minus 1 rounds and the last 1 round. And for the last round, we further guess the input differences for ES boxes. And for the first L round, we introduce 3 ML variables to represent the output differences. So we only consider the case when the linear equation system is underdetermined. In other words, the number of variables is larger. Sorry, I guess I made a mistake. So the number of variables should be larger than the number of equations, because if it is not underdetermined, we can directly use the technique at Crypto 2021, and we cannot increase the number of attacked rounds. Why may wonder that for an underdetermined linear equation system, the time complexity to enumerate all possible solutions is lower bounded by its number of solutions. So intuitively, we cannot improve the attack, but we should be aware that these 3 ML variables are not independent. So we have the chance that there is only one solution to this underdetermined linear equation system if we take these additional nonlinear relations into account. So how to do it? First, we need to do a pre-processing So we first can construct the coefficient matrix M for F, and then we know that the linear equation system is parameterized by M, alpha and gamma, where alpha is computed from delta R0, and gamma is the challenge computed backwards. Then we can split M into M0 and M1, where M0 represents the first Q columns of M. Then we apply Gauss elimination to M1 until it becomes the reduced row echelon form and denote the transformation matrix by Q1. By applying Q1 to the original linear equation system, we obtain an equivalent linear equation system. And we also can know that the last omega rows of this matrix are all 0 because we reduce it to the reduced row echelon form. And so we will obtain omega linear equations only in terms of the first two variables. And we can, these equations can be parameterized by the coefficient matrix P0 prime, epsilon prime, and beta prime, where epsilon prime can be computed from alpha and Q1. Beta prime can be computed from the challenge gamma and Q1. Then, as the offline phase, we can make Q equal to 3t. In other words, we consider the variables representing the output difference of the first TS boxes. And then there will be only 2 to the 1.86t possible values of these 3t variables. Note that, let me say so as I said before, these variables are not independent. This indeed shows this, because if these variables are independent, there will be 2 to the 3t possible values. But now there are only 2 to the 1.86t possible values. So we have the chance that there is only one solution to the undetermined linear equation system. That's why we can improve the attack for low MC. And so then for all possible values, we can compute beta prime and store this tuple in a table. And we should know that beta prime is an omega bit value, and hence in this table, each beta prime will correspond to 2 to the 1.86t minus omega different values of D1, D2 until D3t, and the memory complexity is 2 to the 1.86t. At the online phase, then for each challenge gamma, we can compute the corresponding beta prime, and then we can compute the index, the D1, D2, D3, and D3 until D3t from the pre-computation table DU. And then we solve the first m minus 3m plus 3e minus omega rows of the following linear equation system, because we have considered the last omega equations already as the offline phase. And there are only 3ml minus 3t variables because the 3t variables have been pre-computed. And we use it as an index. Then by some analysis, we can know that given each challenge gamma, we will have so many solutions of the variables D1, D2 until D3ml. In other words, for each challenge gamma, we need to verify so many different transitions in the middle R1 rounds. So the time complexity of the offline phase can be formulated like this. So this is the time complexity for the background difference enumeration. And this is the time complexity for the backward difference enumeration plus so many state difference transitions in the middle R1 rounds. So we can have some constraints on these parameters to make our attack meaningful, because we have to be faster than brute force. So let us consider some concrete examples. So if there is only one S-box per round, we can see that the memory complexity was improved when compared with difference enumeration attack. And so you can see it from here. And when there are only 10 S-box per round, we can also know that the memory complexity was also improved, especially when the block size is much larger than the key size, we can extend the number of maximal R1 because with the previous two attacks, the maximal value of R1 cannot be reached. So the 368 cannot be reached. So we extend R1 by using additional memory. And due to our algebraic meet in the middle method, we have more candidate chairs left. So we need to further optimize the time complexity to retrieve the key. So we will use some properties of the low MC S box. One property is that if the S box is active, we have two linear conditions on the input bits, and the S box will be freely linearized. And one property was that we can have 14 linearly independent quadratic equations to describe the S box. So we can after a candidate chair is recovered, we can perform the key recovery with this procedure. Specifically, we can initialize two counters A and B as 0, where A and B denotes the number of active and inactive S boxes per round. So we can see it from this figure that, so we start from the cipher test pair, and then we check the S box round by round and one by one. If the S box is active, we increase A by 1, and the S box will be freely linearized. And if the S box is inactive, we increase B by 1, and we introduce 3 intermediate variables to represent its input. So, and we will have 14 quadratic equations. So we will have so many leading equations, so many quadratic equations, and so many variables. And we constantly check whether such an equation system can be solved with the linearization technique. And to make our attack more efficient, we only consider the conditioned differential candidate chairs, and the success probability of our attack is about 0.5. And the time complexity is reduced to constant time when compared with the number of bit operations of the low MC encryption. And you can see from this, the last column of this table, that we can significantly reduce the security margins of the low MC parameters, especially when the block size is much larger than the key size. We can break them and even break much more rounds. And we can also reduce the security margins of the backdoor cipher low MCM, and the security margins are further reduced. In summary, we propose new algebraic attacks on low MC, and the attacks are highly related to the feature of partial nonlinear layers. It seems to reveal that the partial nonlinear layers are still not well understood, and the key recovery was also improved by solving an O-defined quadratic equation system. And finally, I want to mention a problem whether we can further improve the attack. For example, can we extend R2 because in all the attacks, we have the same constraint. So that's all, thank you.
Thank you very much. Are there questions on site and online? First, on site. Let's click online.
It was a little fast for me, part of it. I think I didn't catch something. You were saying a linearization was your technique for solving the quadratic system. Is that what you're saying? Is that something that's optimal in your framework, or could you use something that requires like a reduction to normal form or something? Might that be an improvement?
So because after a differential chair is recovered, we have the capability to construct such an equation system, and almost for free. We only need to check the S box is active and inactive, and we can easily construct such an equation system that can be easily solved. So we do not need to do something like computing the global basis or something like that. It's very costly. We only need to do the Gaussian elimination. Yeah.
Right. Thank you.
Any other questions? Okay, so let's thank the speaker again. Okay, so the next talk is called Latin Dances Reloaded, Improve Cryptanalysis against Salsa and Cha-Cha and the Proposal of Oro. So it's, yeah, I will read it already. So it's by Murilo Cucino, thank you, Iago Pasos, Juan Grados, Fabio de Mendonça, Rafael Timoteo, and Fabio Borges, and Juan will give the talk.
Hello. Okay. Hello. So the title of this word is Latin dance reload, improve cryptanalysis against salsa and cha-cha and the proposal of Forró. This work is work together with Murilo Coutinho, Iago Passos, Rafael Sousa, Fabio Borges. They work in Brazil, and I am Juan Grados, working in the Technology Innovation Institute in UAE, Abu Dhabi. So first, it is the agenda for this talk. First, I'm going to talk about some brief introduction about salsa and cha-cha, and after that, which are the best techniques against these two string ciphers. And after that, I'm going to talk about our contributions, specifically about the cryptanalysis that we did against salsa and cha-cha. And after that, I'm going to present a cipher called Forró, a new cipher, and finally our conclusion. So regarding to salsa, as we know, salsa is a cipher invented by Daniel Bernstein in 2005, and this cipher was constructed as alternative to AES, consists of 20 rounds, is fast in software, and is a string cipher, as ARX cipher, and you can generate 2 to the 64 streams by using this cipher. So after that, in 2008, Daniel Bernstein modifies salsa in order to have better diffusion. And this cipher is being used now in the TLS version 1.3. These two ciphers are resistant against timing attacks and cache attacks due to the inherent properties of these ciphers in his construction, because they are using ARS components. So let's see some state of the art. We have several papers across along the years, cryptanalyzing salsa and cha-cha as well. Okay, and one of the most remarkable papers is this paper from Amazon et al. Presented at Fast Software Encryption 2008, because they reached for the first time 8 rounds of salsa in the key recovery setting. So this is a very remarkable paper, because the other papers, more recent papers, only improve the complexity of this attack, but they don't go further in the number of. So regarding to salsa, to cha-cha, similar, we have this paper for Amazon. This paper is a paper that reached 7 rounds of cha-cha, okay? And after that, the following papers only improve the data complexity or time complexity. Okay, so because this paper is one of the most important ones, and actually we already used this paper in our paper, I'm going to talk about this attack presented by Amazon. This is a probabilistic neutral bit attack. So this probabilistic neutral bit attack basically is an attack in the to mount key recovery. Okay, so in the key recovery, usually you have a distinguisher. So here I am representing the distinguisher, for example, for cha-cha with only 3 rounds. Okay, and in this distinguisher, I am representing the correlation of this distinguisher, but epsilon d. So after that, in the key recovery attacks, you need to analyze a few rounds after that distinguisher. So in this case, I am analyzing, for example, in this example, we are analyzing two rounds. Okay, and there is a claim in the Amazon paper saying that you can verify the correlation of this distinguisher by using the inverse of the K-strength generation process, and also by using the inverse of the permutation. By using this, you can verify this correlation. So, so one of the first steps of this attack is try to identify which bits doesn't have influence or have a very low probability influence to compute the correlation of this distinguisher or this value epsilon bit. So if you identify these bits, actually you can, of course, try to discard these bits, and in this way you can do, for example, a brute force with better complexity. Okay, of course there is some formulas to compute the exact complexities that are in the paper of Oman. So another attack that is very powerful against salsa and cha-cha is this differential linear attack against salsa and cha-cha reduced to 7 rounds or 8 rounds. Okay, so this differential linear attack, basically you need to divide the cipher in 2 parts. Okay, in the top part you basically need to find a differential distinguisher. In the linear part you need to find a linear distinguisher, and after that you need to connect these two parts by using for example a DCT. Okay, and I am representing this part in the middle that is called the name middle part. So I am representing here the probability of the differential by P, the correlation of the middle part by R, and the correlation of the linear part by Q. So the correlation of this attack will be of the distinguisher will be PRQ squared. And to distinguish a cipher of a pseudo-random permutation, you need this number of steps. So as you can see here, the factor of the linear part, the factor of the linear part is the most expensive one, because we are seeing here the exponent 4. So because of this, most of the papers analyzing cha-cha or salsa as well, even in our paper, we study the linear properties of modular addition. Okay, so one of the first linear properties is one that mostly us knows probably is this one involving the less significant bits of the input and the less significant bit of the output, and this is the expression. Another property is involving 2 consecutive bits of one of the inputs and one bit of the other input and 1 bit of the output, and this is the expression, and this happens with probability 3/4. So now I'm going to talk about our contribution. So by looking at these 2 linear properties that I just mentioned, and looking also in the formulas of the quarter round of cha-cha, we managed to improve the number of lemmas, the number of rules presented by previous papers, as for example, Chowdhury and Maitra and Coutinho, Asiacrypt 2021. Okay, so by using only 3 rules, we managed to generate all the previous rules to find linear approximation with high correlation. Okay, so by using this linear approximation with these only 3 rules, we managed to construct an attack against 7 rounds of cha-cha in the following way. We first use a truncated differential proposed by Coutinho and Sousa, that's a paper presented in 2020 that is in the print, and this truncated differential has a probability 2 to the -11. Okay, and for the linear part, we use our tool that we implemented in this tool, these 3 rules that I just mentioned, and by using this tool, we managed to find this correlation 2 to the -53. So the complexity then will be 2 to the 214. This is an improvement of 2 to the 10 compared with the previous best known attack. Okay, regarding to salsa, to cryptanalyze salsa, we we developed a technique called bidirectional linear expansion. In this technique, we basically observe which are which are the diffusion properties of salsa and cha-cha. As you can see, the diffusion properties of salsa or cha-cha, if you look, for example, for differential or linear approximations with a high probability or high correlation, you will see that in general, for a few rounds, those differential or linear approximations with only a few active bits in the input or in the output have the better correlation, the higher correlation. So observing this, we start our attack against salsa reduced to 8 rounds by only one active bit, activating only one bit at round 5. And after that, we go backward and forward. To go backward, we use the quarter round formulas, okay? And we obtain these 3 bits at round 4. And for the differential part, we use Omoson et al. Truncated differential that happens with probability to the -1. And to go from the output of this one round truncated differential to the round 4, we use some experiments using CUDA and that are also implemented in our tool called Cryptanalysis that later I will show the link. Okay. So to go from round 1 to round 4, we did this experiment and we compute this, we obtain this correlation. So by using the peeling lemma, you can compute the correlation of the input linear mass. You can see here that if you try to do or to compute the correlation directly from round 1 to round 4 without using the peeling up lemma, you will need more than 2 to the 80 samples. So this is a huge number, and this is why we compute the correlation to each bit, and after that we use the peeling up lemma. For the linear part, we use also Cryptanalysis, our tool, and we found this correlation 2 to the -54. So by using now this distinguisher, we can compute the complexity that is 2 to the 215. Okay, and this is the first time ever that someone present, according as far as we know, an attack against salsa reduced to 8 rounds, but only using a pure differential linear distinguisher, a pure distinguisher, not in the key recovery set. So for the key recovery, we use this previous 5-round differential linear distinguisher, and we use the probabilistic neutral bits to mount a key recovery against salsa reduced to 8 rounds. Okay, and this data complexity is 2 to the 113.14, and the time complexity is 2 to the 217.62. And this represents an improvement of 2 to the 32 compared with the previous best attack in the key recovery settings against salsa. So now I'm going to talk about forró. Forró is a Brazilian dance. Okay, it's also a Latin dance, like salsa and cha-cha. And forró, to construct forró, we basically observe the number of components of salsa and cha-cha. As you can see, the number of components, including all the components, rotation, modular addition, XOR operations, are 12. So by using this and by using advice of Daniel Bastin that is presented in his paper in 2008, that he said, replacing some of the rotation with a comparable number of additions might achieve a comparable diffusion in less time. So by using these 2 facts and a craft design, we can up with this cipher called forró. So this cipher called forró has better diffusion than cha-cha. Okay, so we recommend to use 14 rounds because of this. And this cipher as cha-cha and salsa, also we have a version with this 256 key bits. And now I'm going to explain how is the design for only 2 rounds of forró. So as cha-cha or salsa, we can represent the state of the of this cipher by using a matrix 4x4, where each cell of the matrix is a n-bit unsigned n-bit number. Okay, and now here I'm going to put only 2 rounds. So I'm going to explain how it works for the even rounds and for the on round. As Chacha, we need to go to the columns. We need to apply the quarter round to the column, but we need to choose another word. Okay, which word we are using? We are using the word with better diffusion of the previous quarter round to compute the actual quarter round. Why? Because in the previous quarter round, this word that we are using, we are picking to the next quarter round, is that one with to reach this word, we need to pass across all the components of the quarter round. So this is why we are using this this word. Okay, and we keep doing this for all the columns in this even round. For the odd round, the same. We need to pass always the previous quarter round with better diffusion, and we keep doing this up to the end of the round. But as in Chacha, we are doing this by diagonal. Okay. So regarding the security and performance, we reach up to 5.25 rounds again for row. Okay, by using the state of the art. So we use also differential linear attacks to analyze the security of a row. And regarding the attacks in the key recovery setting, we also combine differential linear attacks with probabilistic neutral bits attacks, and we reach 5 rounds of a row. We reach this quantity of round, and we implemented for row in several hardware architectures. Okay, and we see that for example, ARM architectures, for row has a slightly better diffusion than salsa and chacha. Okay, but that doesn't happen in the Intel architecture. Why? Because in the Intel architecture we have this technique called speculative technique, where the Intel basically manage or predict which instructions will or can execute in parallel, and this is something inherent to the rounds of Chacha and Salsa, because in Salsa and Chacha you can apply the quarter rounds in parallel way. So in for row we sequentialize the round. So this is why for this architecture for row is slightly worse than Chacha and Salsa. Okay. Okay. Now, finally, the conclusions. Okay, we present a new technique to attack Salsa. We reach 8 rounds by using this differential linear distinguisher. Okay, and we present also. I present 8-round an attack against Salsa, reduced to 8 rounds, and we managed to improve the previous word by a factor 2 to the 32. We are using, in the case of Chacha, we are using or trying to improve the number of lemma of previous words. Okay, and our attack is 2 to the time faster than the previous no attack. Always reduced to 7 rounds. Okay, here in Chacha. We are looking forward to apply our techniques also to Chasqui, for example, that is also an ARX cipher. And I present this cipher called for row that has better diffusion than Chacha. And here is the link of our tool called Cryptanalysis that is in GitHub. Well, thank you.
Thank you very much. Are there any questions on site? And online. Oh, there is one in the chat. Okay, so yeah, then I have a question. So you say you're looking forward to apply your techniques to other ciphers. Do you have any specifics in mind?
Yes, for example, yes, for example, we are thinking to apply to Chasqui. This is one of the proximal next work.
Okay. Any other questions? Yes.
Thanks for your presentation. So in your work, it seems to use a new approximation for the modular addition, right?
Yes.
Yeah, so maybe there are some underlying assumptions like independency because you
Yes.
approximate for many rounds.
Yes.
Have you verified them experimentally?
Okay, nice. Thank you for the question. We have in one of the slides this transition from round 1 to round 4. I think you are asking because of this. Yes, we did some assumptions regarding the independence. But actually, because the number of samples that we need to verify this transition is so high, we needed to split our experiments to the round 1 to the round 4 bit by bit. But to verify if that really works, we did some few experiments also by in a small number of rounds. So using this, we managed to find this correlation.
So you mean for a small number of rounds, it matches your theoretical analysis?
Yes.
Okay, so okay, that's all. Thank you.
Okay. Any other questions? Okay, let's thank the speaker again. The next talk will be given online. Okay. Okay, so the next talk is called Mind the Tweaky Schedule, Cryptanalysis on Skinny E 64-56. It's a paper by Lingui Qin, Zhaoyang Dong, Anyu Wang, Xiaoling Yu Hua, Xiaoying Wang. Sorry for the pronunciation, I apologize. And Lingui will give the talk online, if that works. Yes. So please go ahead.
Okay. Hello, my name is Lin Yueqin. Today, I will talk about our paper, Mind the Tweaky Schedule, Cryptanalysis on Skinny E 64256. This talk includes the following 4 parts. First, we briefly introduce the background and our contributions. At Asiacrypt 2014, Jane et al. Proposed the tweaky framework for tweakable block ciphers. They consider the tweak and the key inputs in a unified manner as a tweak key. A subclass of tweak key for AES-like ciphers, named as the STK construction, is shown in the figure. Many designs of tweakable block ciphers are proposed, such as Deoxys, Skinny, and Craft. Skinny is a family of lightweight cipher, following the tweaky framework and the STK construction. There are 6 main versions due to different block size n and tweaky size Zn. In each round, the state is updated with 5 operations, subcells, add constants, add round tweaky, shift rows, and mix columns. An important difference between the STK and skinny is that in the Turkey schedule, the cells of the Turkey are updated by LFSR instead of multiplying an coefficient alpha in the finite field. Then at Eurocrypt 2020, the threshold implementation friendly cipher Skinny E64256 extends the design of Skinny to support the 256-bit Turkey to meet the requirements for the TI-friendly AE modes. It applies the same round function but a new Turkey schedule. However, the security claim may not hold due to the new Turkey schedule. In response, the authors proposed an updated version 2. In this paper, we give a formal analysis of relations of subturkeys to clarify the properties of the new Turkey schedule, especially the difference cancellation property in the differential lag distinguishers and the relations of subturkeys. By exploring the properties in the rectangle attack, meet in the middle attack, and the impossible differential attack, we discover unexpected distinguishers or K-recovery attacks. Further, we propose a uniform design strategy for Turkey schedule of any z equal to or less than 14. Our schedule satisfies the security requirements with a formal proof. Second, the properties we found for the new Turkey schedule. In the Turkey schedule of Skinny E64256, the 256-bit Turkey is viewed as 4 times 4 square arrays of nibbles as TK1 to TK4. In each round, a permutation P is applied to each nibble of all Turkey arrays. Then apply the LFSR to update each nibble of the first and second rows of TK2 to TK4. The difference between the Skinny E64256 and its version 2 is the LFSR used for the TK4. Since the Turkey schedule is linear, we can drive the subturkeys from the same nibble of the master K as a system of linear equations, where Li is a 4 times 4 binary matrix corresponding to each LFSR. We can use A with index R1 to Rt to represent the coefficient matrix. The rank of the coefficient matrix A is almost constant. When the rank is A, the image space represents the solution space of those subturkeys, which is 2 to A, and the kernel space is related to the difference cancellations, where the subturkey differences are set to 0. For example, for 4 consecutive subturkeys in round 0, 2, 4, 6 from the same as nibble, the rank of the coefficient matrix is 14. For a fixed master K, there are 2 to 14 possible solutions of the 4 subturkeys. If we set the sub-K differences to 0, there will be only 3 non-zero solutions of the master K difference, which let the difference cancellations happen in the 4 subturkeys. We want to analyze the relations of the rank for different matrices. We found that for some matrices A corresponding to each different indexes, they have the same rank. So we introduce the rank equivalent property, where 2 subsets satisfy some equal difference relations. We call them a rank equivalent. Then we define the rank equivalence class. For any rank equivalent subsets X and Y, the rank of AX is equal to the rank of AY. We find when T is greater than or equal to 4, certain sets of index will lead to non-full rank coefficient matrix. Then we count all different rank equivalence classes of non-full rank and list parts in the table. For Skinny E64256 version 2, the coefficient matrix is always full rank. For original Skinny family, when Z is equal to 2 or 3, for a given active Turkey cell, subturkey difference cancellations can happen Z minus 1 times in every 30 rounds. For Skinny E64256, the non-full rank properties can lead to more subtractive difference cancellations than expected. When the matrix is full rank, the size of its kernel space is 1. Then the master K difference has only one zero solution, which is not active. When the matrix is non-full rank, the master K difference have non-zero solutions, which means the subtractive difference cancellations can happen. So using all the non-full rank equivalence classes in the upper table, we summarize several different cancellation behaviors. When T is full, all the matrices are non-full rank. That is, for the given active nibble in the master K, the difference cancellations can happen 4 times in arbitrary rounds for every 13 rounds. When T is greater than or equal to 5, O rank is 15. There is only one non-zero solution of the master K difference. For some different rank equivalence classes, the solutions are same. For example, the solutions of the 2 listed equations are same. That is, for the same master K difference, the cancellations will happen at the positions corresponding to the 2 index sets at the same time. At last, there are totally 2 kinds of difference cancellation behaviors, where the subtractive difference cancellation happens 7 or 8 times in the fixed rounds of every 30 rounds. In K recovery attacks, several rounds are added before and after the distinguisher, and the involved subtractives should be guessed to recover the master K. Following similar idea of the key bridge technique, we can use the relations of subtractives to get more accurate and efficient K-guessing strategy in the K recovery phase. For example, assume that a sum of subtractives derived from the same nibble are to be guessed. The number of possible guessings is determined by the rank. For example, the number of possible values for the first RT subtractives is 2 to A. Then after guessing the RT subtractives, the number of possible guesses for the last nibble is 2 to B minus A. Then applying those properties, we analyze the security of skinny E64256 and its version 2. The boomerang attack uses 2 short differentials to construct a longer distinguisher. Then the boomerang attack is developed into the rectangle attack, which require only chosen plain text queries. It's a powerful cryptanalytic technique for skinny family in related key setting. There are several K recovery frameworks of rectangle attack. Inside, Dong et al. Proposed a new related key rectangle attack for ciphers with linear key schedule. They try to guess all subtype keys involved in EB and part in EF. Then with partial decryption, they may gain more inactive bits from the internal states as filters to reduce the time complexity in the K recovery phase. We follow Dong et al.'s attack framework, tweaking their automatic model by adding the difference cancellation behaviors and searching the whole rectangle attack. The automatic models are divided into 2 cases according to different difference cancellation behaviors and search for suitable distinguishing. When T is less than or equal to 4, the number of cancellations is restricted. When T is greater than or equal to 5, the positions of cancellations are fixed to 2 cases. In the 30-round distinguisher we found, there are 8 cancellations in every 30 rounds. Then adding 4 rounds before and 7 rounds after the distinguisher, we can attack the 14-1 round skin E64256. The time complexity in the K recovery phase can be further reduced by the K relations involved in EB and EF. We also apply the non-full rank property of coefficient matrix to improve the MTM attacks in single turkey setting and the related key impossible differentials. Recently, several automatic models on MITM attacks are presented. At Crypto 2021, Dong et al. Developed the MILP model for MITM K recovery attack on Skinny. Combining their model and our new discoveries on the key schedule, we developed an MITMK recovery attack on 31-round Skinny E64256. The impossible differential attack uses a differential with probability 0 to act as a distinguisher. We search out a 21-round related tacky impossible differentials on Skinny E64256. We summarize the cryptanalytic results on Skinny 64 and compare with ours. Our cryptanalysis proves that Skinny E64256 doesn't keep a similar security margin as expected by the designers. For example, our attack leaves only a 3-round security margin for Skinny E64256, where there are 11 rounds for Skinny 64128 and 9 rounds for Skinny 64192. In addition, we also analyzed the updated version 2. The attacked rounds keep the same rate as expected by the designers. At last, we give a proposal for tacky schedule of Skinny family. The STK construction supports arbitrary length of tacky, but the Skinny family and Skinny E supports up to 4 n-bit tacky. Skinny with larger tacky size may be useful in future applications. We propose a uniform design strategy for tacky schedule of Skinny nZn for positive integer z less than or equal to 14. To satisfy the subtacky difference cancellation property for given cell position, z-1 cancellations can only happen every 15 rounds for TKZ or every 30 rounds for Skinny nZn. The coefficient matrix should satisfy the block MDS property, where the determinant of the coefficient matrix is not 0. Our construction is an extension of the generated matrix of the RS codes. We set L1 to the identity matrix and choose the Li to be the consecutive powers of a matrix L. When the L satisfies specific property, we can give a proposition to guarantee the block MDS property. One simple way is taking L to be the companion matrix of a primitive polynomial. In our example, we found that the LFSR for TK2 and TK3 coincide with the original LFSR in Skinny, and the LFSR for TK4 coincides with that constructed in Skinny 64256 version 2. From this point of view, our construction can be viewed as a natural extension of the original Skinny 64 and Skinny E64256 version 2. How to choose Li to optimize the implementation efficiency is an important issue. One direction of optimization is to minimize the total number of XORs required by the LFSR. We enumerate all possible L and alpha and list the optimal number of XORs required in the table, for Z from 4 to 7. Another direction of optimization is to minimize the circuit area of the LFSR. In our construction, the minimal implementation is only 1 L, and computing others iteratively, where the area is 1 and the latency is 6. We also propose an area latency trade-off to reduce the latency by slightly increasing the area. All construction can be naturally intended to choose C times C matrix such that the block MDS property is also satisfied. That's everything I want to talk about. Thanks for your attention.
Thank you very much. Are there any questions on site first? Online, maybe? Okay, then I have a question. So you propose a new tweaky schedule. Can you give us some feedback of the performance impact it can have on the block cipher itself?
You mean the proof of proposition?
Yeah, your proposition, what would be the performance impact you would expect?
Well, the basic idea is we give some direct computation method of the determinant of the block one-element matrix. Then using the property of the eigenvalues, which are not 0 or 1, we can accomplish the proof.
Okay, but will this slow down to skinny or?
Skinny? Sorry, pardon?
So what would be can you evaluate the impact on the performance of the block cipher?
Performance? Okay.
Okay. Did you try implementing one of them and see what would be the performance impact?
No, we just
okay.
give the
Okay.
experiment. Okay.
Any other questions? Okay, let's thank the speaker again.
Okay.
So the next talk will be online again. It's called Enhancing Differential Neural Cryptanalysis. It's by Zhenzhen Bao, Yuan Guo, Meicheng Liu, Lima, and Yi Tu. And Zhenzhen will give the talk. You can share your screen. Are you online? Okay. Okay, thank you. We can see your slides. The floor is yours.
Hello, everyone. Can you hear me? Sorry.
Yes. Yes, we can hear you.
Okay, sorry. This work is on enhancing differential neural cryptanalysis. It's joint work with Jian Guo, Meicheng Liu, Li Ma, and Yi Tu. I'm Zhenzhen Bao. The differential neural cryptanalysis was proposed by Gore in the seminal work in Crypto 2019. In the improved key recovery framework, a classical differential is combined with a neural distinguisher. Besides, a highly selective key guessing strategy was used. In the framework, the neural distinguisher is built by training neural networks to distinguish two types of ciphertext pairs, pairs whose corresponding plaintexts have a specific difference, and the pairs whose plaintexts are randomly selected. Thus, the neural distinguisher were trained with the principle of differential cryptanalysis in mind, but different from classical differential whose output difference is specified. The neural distinguisher accepts ciphertext pairs. The target cipher is the smallest version of the lightweight block cipher spec with a 32-bit block and 64-bit key, which is an arc cipher. That is, it used modular addition for nonlinearity, used rotations, and XOR for diffusion. Its training data is a ciphertext pair transformed into a quadruple of words. Among the training data, half are positive and half are negative, given the labels 1 and 0, respectively. The neural network structure is the commonly used deep residual network. And 3 training schemes were used to obtain up to 8 round neural distinguishers. A trained neural distinguisher will give a score between 0 and 1 for each unlabeled ciphertext pair, which is equivalent to a probability indicating how likely it predict the given data is positive. When it is larger than 0.5, we say it's pretty positive, otherwise it's pretty negative. According to the real labels, the accuracy of the distinguisher can be evaluated. These neural distinguishers are shown to have superior accuracy than the full differential distribution-based distinguishers. and they use features not represented in the difference distribution table. So using this unlist under the improved key recovery framework with comparable data complexity, the time complexity of the attack on 11 rounds of spec 3264 was reduced considerably. So this goes into the next questions. To what extent is the advantage of differential neural cryptanalysis over traditional methods, and whether the advantage generally exists in the cryptanalysis of modern ciphers? To answer the first question, we devised differential neural attacks on more rounds of spec 3264. We found that the previous differential neural attack is not optimal. By enhancing it, the 12-round attack can be improved. And moreover, a practical key recovery attack on 13 rounds can be achieved. Accordingly, differential neural cryptanalysis has more potential than it initially exhibited. However, the method developed to enhance the attack are on its classical component, that is, deeply exploring the neutral bits. The motivation is to boost the weak signal from the distinguishers. When we look closer at the distinguishers' response, we can see that the distribution of responses on positive and negative samples are largely separated for 5 and 6 rounds. But with the increasing number of rounds, the two distributions are hardly separated. Fortunately, when combining scores of multiple samples of the same attributes, that is, multiple positive or multiple negative samples, and to get a mean score using a formula like this, the accuracy can increase effectively. For example, for 7 rounds, combining 2 to the 1, 2 to the 4, 2 to the 6 scores from the ND on same attribute samples, the distribution of the combined response are gradually concentrated, so the distribution of positive and negative samples can be largely separated. As for the weak 8th-round neural distinguisher, it's required about 2 to the 12 scores on the same attribute samples for the distribution to be separated. However, gathering samples of same attribute is not trivial in the differential neural key recovery framework. That is because of the prepended classical differential, which is probabilistic. That is how the concept of neutral bits is invited by Gore to this framework. The neutral bit is first introduced by Biham and Chen for attacking SHA-0. It has many extensions and related concepts, including message modification, kernels, Bowman runs, probability neutral bits, and free bits. For an arbitrary conforming pairs of a differential, flipping a neutral bits of both of the plaintext, the resulting pair will also conform to the differential. Or this is held with a high probability, for which case we say it is the probabilistic neutral bits. With B neutral bits, one can get a structure of 2 to the B data pairs conforming do not conform to the CD together. The more neutral bits of the prepended CD, the more the same attribute samples could be generated and combined to boost the weak signal from the distinguisher. However, generally, the longer the CT, the fewer the neutral bits. This bar shows the neutral probability of each bit for a one-round differential, where this star marks the position of active bits of the input-output difference of the modular addition. These are for the 2-round differential trio that is used in Gore's 11-round key recovery attack. This is the situation if we extending one more round, one can see that there is no high probability neutral bits anymore. The number of neutral bits naturally depends on the number of rounds, but also depends on the distribution of active bits of the differences in the dominant differential trio. For example, this is the situation for 1 round, 2 round, and 3 round of another differential trio. It is suboptimal but have more neutral bits. So this trio is used in all attacks. Still, these neutral bits are not sufficient. So two types of generalized neutral bits are considered beyond that considered in Gore's work. The first type is the simultaneous neutral bit size. That is when for differential given a conforming pair flipping individual bits, the conformability might be changed, but simultaneously flipping a set of bits does not change the conformability of the resulting pair. So take the above differential trio as an example. This is the situation of 1 round, this is of 2 rounds, and this is the situation of 3 rounds, where this pink bar shows the neutral probability of flipping both the S bit of Y and the I+7 bits of X. And this velvet bar shows the neutral probability of flipping the S bit of Y, the I+7 bits of X, and the I+1 - 7 - 2 bits of Y. So we get more generalized neutral bit size, but still they are not sufficient for boosting the weak signal if the 8th round neural distinguisher is used to attack more rounds. So we introduced the conditional simultaneous neutral bit size. That is, a set of bits is neutral for conforming pairs that fulfill some constraints. To find them, we investigate how the neutrality of each candidate's bit set is influenced by the values of bits in some involved and controllable variables. For spec, the concerned variables are those involved in the first modular addition. Specifically, they are x, y, and x rotate by 7 position x or y. We observe that some probabilistic neutral bit size are neutral for some conforming pairs when these conforming pairs have some specific bits are almost constant. For example, the bit size y5 and x12 is neutral with probability 0.5. When it is neutral, the corresponding conforming pairs always have this bit XOR to 1. But overall conforming pairs, the probability of this bit B1 is around 0.5. So we deduce that the condition for the bit set Y5, X12 having neutral probability 1 is having those conforming pairs with this bit XOR to 1. So with a automatic procedure and experimentally evaluate the conditional neutral probability of candidates bit size and find their conditions. For example, this blue bar with a green border shows that the neutral probability of bit set X5, X15, Y15, X6, X8 is almost 1 in the condition that Y1 equals 0. And this bar it shows that the neutral probability of Y4, X11, X13 is around 0.91 in the condition that Y4 XOR X11 equals 1. In addition, we found that it's possible that given an arbitrary conforming pairs of one differential, flipping a bit and adjusting the input difference, one get a conforming pair of another differential. They share the same output difference. The conforming pairs of the two differentials are one-to-one correspondent by this bit. Thus, the probability of the two differentials are the same because these two differentials are adjoining differentials and call these bits the switching bits for them. Such as switching bits can play the same role as the neutral bits for doubling the size of a ciphertext structure. Besides, we found there are differentials that share the same output difference, have exactly the same set of useful neutral bit size, and the difference of their input difference is one of their common neutral bits. Then, once the pair of input pair is generated using the neutral bits for one differential, one can repair the inputs and obtain a pair of input pairs for the other differential. And thus, by repairing, one can reuse the data to double the number of ciphertext structures. Since one has to guess a few qubits to use the conditional neutral bit size, we extend the differential neural key recovery framework with an outer loop of guessing a few qubits. The core of the attack is the same as the GERS improved key recovery framework. It employs an R-round mean and R-1 round helper neutral distinguisher trained with data pairs corresponding to an intermediate difference, a short classical differential or multiple of differentials whose output difference is the input difference of neural distinguisher is prepended. Data pairs with this input difference are generated. Generalized neutral bits of the CD are used to expand each data pair to a structure of data pairs. The resulting structure of data pairs are decrypted by a free round and then query to obtain the corresponding ciphertext structures. Each ciphertext structure is used to generate candidates of the last subkey with a highly selective key search policy. More specifically, the key search algorithm depends on an important observation. That is, for the target cipher, the wrong key randomization hypothesis does not hold when only one round of trial decryption is performed. The expected response of the distinguisher upon wrong key decryption will depend on the bitwise difference between the trial subkey and the real subkey. This wrong key response profile, which can be pre-computed, is used to recommend new candidate values for the subkey from previous recommended values by minimizing the weighted Euclidean distance. It recommends a set of subkeys and provides their scores without exhaustively performing trial decryption. The use of the ciphertext structure is also highly selective, using a standard exploitation technique, namely upper confidence bound. Each ciphertext structure is assigned a priority according to the max score of the subkeys they previously recommended and how often they were visited. The score of the recommended subkey is the combined response from the neural distinguisher on ciphertext pairs in the ciphertext structure. This score is highly selective, decisive for the execution time and success rate of the attack, because it will determine whether the recommended subkey will be further treated as its score passes the cutoff, and the maximum one also determines the priority of the ciphertext structure. This is the detailed information on experimental results for attacking 13 round. And this is the information on attacking 12 round. So they are the application of this unorthodox key recovery phase. Alongside this, we provide substantial illustrations to unveil previously hidden details of this unorthodox key recovery phase, including the distribution of the maximum score of candidate subkeys recommended by the wrong ciphertext structure and the right ciphertext structure, and the percentage of the maximum scores passing various of cutoffs. Observations derived from these illustrations provide rules of thumb for turning critical parameters, especially the cutoff C1, which determine the time complexity and success rate. To answer the second question, we produce various neural distinguishers on round-reduced Siemens 3264 and provide comparisons with their pure differential differential-based counterparts. We note that unlike spec, for Siemens, the R-round distinguisher accept values of ciphertext pairs should compare with R-1 round distinguishers that accept difference. This is because for Siemens, given the R-round output, Without knowing the key, one can directly deduce the R-1 round difference. The comparison results show that the R-round neural distinguisher accepting values and R-1 round neural distinguisher accepting partial value, partial difference achieve similar but weaker classification accuracy than R-1 round DDT-based distinguisher. We conjecture that R-round NVs that accept values of ciphertext pairs could decrypt one unkeyed round and try to learn the full R-1 round output difference distribution, but fail to learn more features beyond the distribution of differences. Besides using the differential neural cryptanalysis framework, we devised practical key recovery attacks covering 16 rounds. This indicates that the differential neural cryptanalysis should work in general on modern ciphers. Still, their advantage might be either to show on ciphers whose differential-like properties cannot be accurately evaluated using existing tools. And we think enhancing the connection between traditional cryptanalysis techniques and machine learning approaches is helpful for achieving better cryptanalysis results. And these generalized neutral bits, they are not intrinsically linked to neural network-based cryptanalysis, but are expected to be useful for converting a wider range of weak distinguishers to competitive key recovery attacks. The rules of thumb on turning parameters for key recovery phase are far from perfect. A rigorous theoretical model on the relation between attack parameters, attack complexities, and success probability is still missing, the building of which is left as future work. Thanks for your attention.
Thank you very much. Are there any questions? Yes.
Thank you for your presentation. Can you explain your environment for experiment and how to calculate the time complexity and computational complexity?
All of the time complexity are obtained by running the data, the attack and time it. So, and then translate to the equivalent number of encryptions. For example, for the attack on 13 round, we run the attack 40 times on a GPU with the V100 GPU card, and we then time the complexity, the time complexity, and we compare the running time between on a GPU and on CPU. And then translate to if one encryption of 1 second can run 2 to the 28 encryption of spec, then how many encryptions is equivalent to the text. So this is a pure experimental dependent evaluation of the time complexity.
Okay, the processing time of the neural distinction is depend on the computing environment, right?
Yes.
So the performance of your attack is it differs on the computing environment.
Yes. So we make some of the experiments are on CPU, some on GPU, and we try to compute the rate. And also, we think this is an open problem on how to fairly compare the time complexity. And we think a theoretical model, it will be very interesting. So we will left it for future work.
Okay, I understand. Thank you.
Any other questions? If not, then let's thank all the speakers of the session again. This concludes the session.